Yeah, good morning. Thank you, Professor Vasudevan. Let me first thank Professor Arunan for arranging this conference to celebrate 100 years of hydrogen bond, as well as inviting me to give a talk. So I think, it is good to talk after Mukesh, because he has already shown you the importance of this selenium non-covalent interaction using selenium enzymes. It will be helpful in my talk. So what I will do, so I will tell some of our contribution to understand the nature of unconventional hydrogen bond from IR spectroscopy data. So we have seen from our yesterday's talks that this unconventional hydrogen bond is not straightforward like conventional hydrogen bond. It is more complicated, and we think that we have not completely understood it. We know the thing that first concept of hydrogen bond has been given exactly 100 years back by this Latimer and Rothbuss. They explained this taking this ammonium solution in water, and where they have told that this hydrogen nucleus held between two octet constitutes a weak bond. So they have mentioned about hydrogen and weak bond, but I think they did not talk about hydrogen bond at that time. And in the footnote, they of course gave credit to Maurice Huggins, who gave the first idea hydrogen atom can be bonded to two atoms to other atoms at the same time. Then we think that G. N. Lewis coined the term hydrogen bond in 1923, and Linus Pauling in his book Nature of Chemical Bond in 1939, he told that hydrogen bond cannot be called a chemical bond, and this is XHY, which we call hydrogen bond. This XH is a chemical bond. A chemical bond means it is covalent in nature, that is what we know, and this is hydrogen bond, and he told which is electrostatic in nature, but he told that it has very small, about 5% covalent character in hydrogen bond. And then after 60 years from then, in 1999, it was indeed proved from the experiment this covalent character of hydrogen bond in ice from this inelastic X-ray scattering or Compton scattering. So now the thing is that this this covalent character, probably when we go from this conventional to unconventional hydrogen bond, the importance of this covalent character probably increases. It is not 5%, it could be more than that, and which can play a significant role. So that is what I will try to tell you in my talk. We know all these things. This is hydrogen bond, it is very strong when both X and Y are strongly electronegative, and unconventional hydrogen bond, in this case either X or Y could be less electronegative, or both could be less electronegative. And which is most popular in the literature for unconventional hydrogen bond is CHX type hydrogen bond, CHO, which is weak in nature. So now the question is that can unconventional hydrogen bond be strong? This is unconventional hydrogen bond when your hydrogen bond donor is weak in electronegativity, that is the CHO type hydrogen bond, where Professor Gautam Desiraju made a seminal contribution, and this is very weak. And another type where you can change this hydrogen bond acceptor, like let us say in case of sulfur, which is very less electronegative, where these Professor Sanjay Wategaonkar and Professor Himanshu Biswal, they made seminal contribution to understand this type of weak interaction. But what they found that this NHS or NHO, they are of similar strength, and which is very interesting as well as surprising, because from your conventional wisdom, it is difficult to explain that how this NHS also is equally strong to NHO hydrogen bond. And then going further, this Jairgard and co-workers, they changed this hydrogen bond acceptor atom to phosphorus, and there also they found that this OHP hydrogen bond can have similar instant to OHO hydrogen bond. They did with alcohol and trimethyl phosphine, and this is OHP, where this is a positively charged phosphorus, and then it has this sigma hole, and then it makes this strong hydrogen bond this is the green one is the alcohol IR spectrum for OH stretching frequency, and the red one is for this complex which is strongly redshifted. So now now if we talk about this hydrogen bond in terms of this weak donor in terms of electronegativity, I mean that is not very much explored in the literature. Mostly it is limited to this CHY type hydrogen bond and which is weak. So we thought of actually exploring I mean this hydrogen bond with this weak hydrogen bond donor. Then if we go to this hydrogen bond redefinition in 2011, so what it tells this, what is the requirement in XHY, X has to be more electronegative than hydrogen and there is no restriction on Y atom. So that means if you look at the periodic table, this is the electronegativity of hydrogen 2.20. So then whichever atoms have electronegativity more than this 2.20, I mean whatever I have marked here, so they could be I mean potentially this hydrogen bond donor atom, and any atom in the periodic table could be hydrogen bond acceptor. So then you have lot of opportunity to explore this kind of unconventional hydrogen bond. So we thought of actually starting this selenium hydrogen bond, so where we can replace this acceptor atom by selenium, or we can put this sulfur or selenium as hydrogen bond donor atom, or there could be extreme case of unconventional hydrogen bond where both this hydrogen bond donor and acceptor could be strongly weakly electronegative, like you can see their electronegativity almost similar. So the question is that especially in this case are this hydrogen bond very weak in nature or it could be also strong. I mean already Mukesh has explained that the importance of this selenium hydrogen bonding in proteins. There are a few of the examples from PDB. Here you see this NHAC hydrogen bond, and where Himanshu already showed that from PDB analysis, I mean there are more than 4,000 this NHAC hydrogen bond is there in PDB, and this is also for NHS hydrogen bond. So now the thing is that when you look at the protein crystal structure, so you don't know exactly the position of hydrogen atom. So then to tell the existence of this kind of unconventional hydrogen bond, it is better to take this kind of interacting units in isolated condition and to prove the existence of this kind of interaction, and also you can tell the optimum nature of this kind of hydrogen bonds. So then one needs this kind of experimental setup which has actually combination of this supersonic jet expansion, where you can synthesize this weakly bound complex and you can study in absence of other interactions. You can have this laser desorption to study the molecules which are non-volatile, and then this is the heart of the experiment for doing spectroscopy, regionality enhanced multipotent ionization, and also you can do the mass selection using time of flight mass spectrometry. So then basically you can have this mass selected electronic and vibrational spectroscopy of molecules or weakly bound complexes. I will not go into details of the techniques. So what we did actually, we took indole and dimethyl selenide, and in supersonic expansion we can make all different types of complexes. This is the time of flight mass spectrum, this is indole monomer and the indole dimer, and this is indole dimethyl selenide, and you can select the mass channel and record the electronic spectrum using this 1 color or 2 color resonant 2 photon ionization spectroscopy. And by selecting the mass channel of indole, this is the electronic spectrum of indole showing only the origin band, and when you select the mass channel of indole dimethyl selenide, you get this electronic spectrum for this dimer. And now using the this IR UV hole bonding spectroscopy, you can tell that all these bands belong to only one conformer. So that is the thing, you see all the bands gets depleted, that means there is only one conformer of this NHAC complex. So the next question is that, I mean we can try to find out what is the structure of this complex and what is the strength of this hydrogen bond, and this is the IR spectrum using this IR UV double resonance spectroscopy, where you can bring your IR laser prior to the UV laser, and you can tune the IR laser during near your this NH vibrational frequency region, and then you can keep your UV laser fixed to the RTP spectrum band. This is the IR spectrum of this NH band, which comes as 3525 wave number, and when you select the electronic band of this complex and record the IR spectrum, so it is redshifted by about 154 wave number, this NH frequency in this complex, and this is the quantum chemistry calculation, you get the IR spectrum almost in a similar position. So this is about 150 wave number redshifted. So then you can compare with this sulfur and oxygen analog, this with indole dimethyl sulfide and dimethyl oxide, and you see that their binding energy almost similar. But the interesting thing is that if you look at this redshift in case of NHAC, NHS or NHO, they are almost similar. So which tells that the strength is similar. So now the question is that then why the IR redshift in this NH stretching frequency for sulfur, selenium, oxygen is similar. Then what Professor Naresh Patwari and co-worker they explained in this paper that this IR redshift for this XH stretching frequency should be given by electrostatic polarization and charge transfer component, and whereas this your dispersion should control the binding energy or stability. So this is called dispersion stabilized hydrogen bond by Sanjay and others. So what we can do then, we can decompose the interaction energy. So here you see the thing by using this localized molecular orbital energy decomposition analysis. The black one is for indole Me2O, the red is for indole Me2S, and the blue is for indole Me2Se. And it is quite logical. If you see that when you go from oxygen to sulfur to selenium, the electrostatic, the ES is the electrostatic, it is decreasing and the dispersion is increasing. But to explain the redshift, then we looked at the charge transfer component using another decomposition analysis, the ALMO EDA, where you can decompose it into this frozen density polarization in charge transfer, where your all other this electrostatic repulsion and dispersion you can dump into this frozen density. And here this is the component charge transfer, what you see for this is oxygen, this is sulfur and selenium, which is increasing when you go from oxygen to selenium. So then probably this charge transfer can have some contribution to give significant redshift in case of the sulfur or selenium complexes. And then we did some frontier molecular orbital calculation to find this orbital interaction. And if you look at for this indole Me2O complex, this is the lone pair which is delocalized into the antibonding orbital of this NH, and you see this HOMO of this oxygen lone pair, and this LUMO, this sigma star NH, the HOMO LUMO, this gap is about 14 electron volt, and if you go from oxygen to sulfur to selenium, this HOMO LUMO gap is decreasing. That means the orbital interaction is increasing when you go from oxygen to sulfur to selenium, so which can actually kind of support this charge transfer or this covalent contribution whatever is coming up for sulfur or selenium hydrogen bond. So then we looked at this water mediated selenium hydrogen bonding in protein. So this is direct selenium hydrogen bond between two amino acid residues, selenomethionine and phenylalanine. But what we found that in protein there are many cavities are there where only single water can go and fit, and it can make hydrogen bonding among the amino acid residues, and it can stabilize the protein. And then we found in PDB then there are about more than 5,000 this kind of water mediated selenium hydrogen bonding interactions are there. And this is the thing in the protein, I mean there are many pockets are there, many cavities are there, and there are a few examples people have shown that I mean the water can go into those cavities and it can bind with the amino acid residues and stabilize the thing. And there is an interesting this MD simulation where they have shown that I mean whether the single water molecule in protein cavity is stability or instability, because when water is coming from the bulk then it has to lose the entropy, because when it is binding and entropy is decreasing. So then what is happening, this is the thing what they have done from the calculation with this cytochrome P450 CAM complex with this ligand 2-phenylimidazole. This the red one is the water, which you see that they are making 4 hydrogen bond, and water can make maximum 4 hydrogen bond, and then you see the delta G is negative minus 12 kcal per mole, which tells that it is the going into the cavity by doing this 4 hydrogen bond, it is stabilizing the protein. And another case what they did, they deliberately put one water molecule in this cavity, and it makes only one hydrogen bond, and the delta G is positive. So then what they concluded that water, if it goes to the protein cavity, so it can be stabilized if at least more than one hydrogen bond it makes with the amino acid residues in the cavity. So we try to mimic this interaction. So this is one of this PDB where you have this tryptophan, selenomethionine and water. That means this is your indole water, and this you can think of this is as this dimethyl selenide. So we took this indole water and dimethyl selenide, we made this 1:1:1 complex, and so this is the IR spectrum in the indole mass channel. Again this is 3525, this NA stretching frequency, and this is the trimer IR spectrum if you see, This is the 3756 is the water OH which is free, and this OH which is making with selenium this hydrogen bond which is coming at 3453, and this NH which is making with oxygen hydrogen bond is 3411. This is a theoretical spectrum. So, we get exactly that kind of structure where water is breathing between these two kind of residues, and this is the most stable structure we get in the experiment, and which is also probable if you look in the protein. When water goes in the cavity, it makes only this kind of structural motif. And then we looked into again this energy decomposition scheme to look at the charge transfer interaction, and we saw the similar trend in case of this is black is oxygen, this sulfur, this selenium, always charge transfer interaction is increasing, and we tried with the different energy decomposition scheme also. There also see the similar trend is happening from oxygen, sulfur to selenium, this charge transfer is increasing. Okay, the last one is that this extremely unusual unconventional hydrogen bond which is SHS hydrogen bond. This XHY where both X and Y is replaced by this weakly electronegative atom SHS. So, in case of CHO we know it is weak. So, then Professor Gururao they have reported in 2015 that this thiophenol crystal structure is stabilized by this SHS interaction along with this some SS chalcogen interaction, and we looked at in protein also there are this between cysteine and methionine this SHS interaction is there, and we looked at the Cambridge structural database. I mean there are about 72 this SHS interaction is there. It is not lot, but still there are this SHS interaction, and in protein also we looked at in the PDB it is about 400 this SHS interaction is there between this cysteine and methionine. So, there are spectroscopy study of this SHS hydrogen bond. Arunan reported from microwave spectroscopy of H2S dimer where there is SHS hydrogen bond, and interestingly few years before that I mean Professor Sanjay Wategaonkar they actually looked at the IR spectra of this H2S dimer where they probed this free SH as well as hydrogen bonded SH, and from their experiment they found that the redshift about 31 wave number. So, which tells that SHS hydrogen bond is I mean weak. So, we thought of studying this SHS hydrogen bond taking this 2-chlorothiophenol and dimethyl sulfide. This is the electronic spectrum of this monomer, and this is of 2-chlorothiophenol dimethyl sulfide dimer. You see that this bunch of peaks which are coming here. I mean if we do this UV hole bonding spectroscopy, if you fix your UV laser one of the pump UV one of the laser at this one of this band, and you just scan the another laser. So, then if you see the depletion of all these bands, so that means this belongs all these bands belong to this conformer and this belongs to another conformer. So, we got this siege and trans these two conformers where this chlorine is on same side with SH and chlorine is other side from the SH, and in both cases you have this SHS hydrogen bond. Then we try to look at the structure from IR spectroscopy. So, here this is for the monomer we probe the SH band which comes at 2567 wave number, and this the blue one is for the cis conformer. When we recorded the IR spectrum in the SH stretching frequency region, it comes about 154 wave number redshifted compared to the SH in the monomer, and in case of trans it is 2447 120 wave number redshifted. That is a lot. I mean it is almost like any conventional hydrogen bond redshift. So, in case of this SHS hydrogen bond we found, and so then we looked at again compared between 2-CTP Me2O and Me2S. This Me2O means you have this SHO interaction, and this is Me2S is SHS interaction, and we found this from this energy decomposition again this from oxygen is black versus red is sulfur. We found there is a huge increment in the charge transfer component, and which probably can compensate with this decrease in the electrostatic component in case of sulfur to give the strong redshift. And we looked from this molecular orbital calculation also looking at this homolumo gap between this lone pair of oxygen and SH antibonding orbital. This energy gap 12 electron volt and going to this is for sulfur and this is for oxygen it is 14. So, that means in case of sulfur you see the thing the two orbitals when they are interacting the energy gap is less, that means interaction will be more. So, this orbital or charge transfer interaction can contribute significantly to the IR redshift of unconventional hydrogen bond. Oh, sorry. Okay. So, now the conclusion is this direct selenium hydrogen bonding what we found is as strong as any conventional hydrogen bond, And from PDB analysis we found that there could be single water mediated selenium hydrogen bonding between 2 or more amino acid residues, and we found this even single water mediated selenium hydrogen bonding is more than direct selenium hydrogen bonding in protein. And then we studied this model complex taking indole water and dimethyl selenide, and which mimics the whatever the motif or nature of the interaction we find in the protein structures. And then we found the SHS hydrogen bond is a very strong non-covalent interaction, and the large redshift in all these S sulfur or selenium centered hydrogen bond could be explained through significant amount of charge transfer interaction present there. And we believe that, I mean, detailed understanding of this kind of nature and strength of this unconventional hydrogen bond can help in designing drugs and various supramolecular assembly having unconventional non-covalent interactions. And we want to thank the group members who contributed to this work, and the collaborator Dr. M.S. Madhusudan in ISER Pune, who did lot of this bioinformatics work, and Dr. Devasri Ghosh and Dr. Biplav Sarkar, they contributed in some place in some calculation, and for funding ISER Pune and ACRB, and thank you for your attention.
NH selenium interaction is one of the references you showed, over 4,000 interactions, right? Are there with the proteins, because only 25 selenoproteins are known in human and only 2 structures are available. So is that with small molecules or in the
No, it is in the protein where people actually replace the sulfur with selenium for actually they replace selenium due to the phasing, crystallographic phasing problem. Yeah, that is the thing.
Okay.
These are all artificial.
Okay.
Artificial.
Okay.
Yeah.
Fine.
Yeah.
Hello. Yeah. So it's quite interesting to see that the new SH is of the order of 150 plus wave numbers.
Yeah.
We have seen this before. DMS is kind of a spoil sport. I don't know why yet.
Which one?
Dimethyl sulfide.
Uh-huh.
You take H2S versus dimethyl sulfide. In H2S, when it is accepted, the shifts are very small.
Yeah.
But if you go to dimethyl sulfide, it's huge.
Yeah.
We have seen that in the NHS first NHS interaction paper in dimethyl sulfide.
So due to
So
the methyl group, proton affinity increases.
So that's one thing. Second thing is, in that thing, what is the starred complex there?
Oh, the star means when you did that whole burning. So
that means it's the third complex.
We kept the this probe laser fixed at this electronic band. For this also. So we are doing UV whole burning. So then on this electronic band, we kept the probe laser wavelength fixed, and we scan the pump like that. That's why I marked that.
So do you see 2 complexes or 3 complexes?
2 conformers are there. Okay, so don't get confused with the start. So all this bunch of peaks are one conformer, and these 2 are also one conformer. If you look at this whole burning, the green, you look at the blue and green.
Okay.
The green, the blue is telling all of them they belong to one conformer.
Which is the major one then? The one which is
the blue one. I mean, this one is the major one, which is giving more redshift.
Okay.
Hello.
Yeah.
Why 2-chlorothiophenol?
Oh yeah, that is a good question, because I mean Himanshu knows and everybody knows. We try to do with thiophenol, but the thing is that the S1 state lifetime is very short due to the conical intersection in the S1 state with other excited state. So that's why we had to take chlorine substitution when lifetime increases. Yeah.
These non-conventional hydrogen bonds are very strong in some cases.
Yeah.
So how do you quantify? Quantify in terms of energy or in terms of?
So we quantify in terms of like because the strength of hydrogen bond you can tell in terms of redshift in your IR band.
Generally we classify based on energies, because very strong means we are reaching the energy window of 10 to 15 kcal. And a strong less than up to 5 or below 5 is weak generally, and most of these cases are 4, 5.
5, 6 kcal.
So,
but I mean,
whether it's right to say it is a very strong hydrogen bond or
not very strong. I mean, they are like, if you take instead of sulfur or selenium, oxygen also if you take, it is giving similar strength, and but energy means, I mean, if you calculate the binding energy, so binding energy will not give you exactly the hydrogen bond energy, because binding energy, if you are the whole molecule, that there are many other components are there.
So did you calculated the hydrogen bond energy or binding energy?
We calculated the binding energy.
So if binding energy is less, then how can hydrogen bond energy could be more than that?
No, binding energy is not less.
5 kcal.
5 kcal. Yeah.
So in that the range of weak interaction.
So in
borderline range of weak interaction.
No, it is not very weak interaction, but
most of the places you are saying very strong. That's what I am.
Yeah, but if you tell this water dimer, so if you take, so this how much is the binding energy and how much is the thing, that is a strong hydrogen bond. Yeah. Okay.
So it can be 10 kilocal per mole. I'll show in the afternoon. It's experimentally determined. I'll show in the afternoon.
Yeah, you can vary it, but this 5 to 6 kcal per mole is not also weak. Yeah. 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 Yeah.
And you assume that the water is a donor. Now I may be biased because I looked at sulfur oxygen direct interaction without any proton anywhere in between. Do you think this water is not really donating, but it is just direct selenium oxygen interaction?
No,
To say that, you have to see other environment. If the water is acting as donor to other protein substrates and fully occupied, and it doesn't have any proton pointing towards the selenium. Whether you have looked at it or you just
we have looked at it when you looked in PDB. So then if it is selenium oxygen, that means the chalcogen type interaction. So then we looked at the distance more than that van der Waals radii of selenium and oxygen, because then you have an extra hydrogen is there. So we looked at from that distance more than that.
Okay, thank you.
Yeah, thanks.